Hi, everyone. I'm Ran Liu from UC Berkeley. And today I'm going to talk about hierarchical GNN and the pooling algorithm designed for it. Nowadays, in order to probe new physics, the energy and luminosity of particle colliders keep upgrading. And I think we just talked about in the previous talk. And this will, of course, lead to a tremendous amount of data to grow far more faster than the computational resources available, which makes a smarter algorithm that scales with event size better become an urgent need. And the Exa.TrkX collaboration utilizes graph neural network technologies to address this issue. So here's the sketch of the Exa.TrkX pipeline. So first, we have to construct the graph via either deep learning approach or statistical approach. The machine learning one, which is the metric learning, uses the multi-layer perceptron to embed hits into an embedding space. And then we impose a potential such that the hits belong to the same particle attracts each other and otherwise repels. And then we build a fixed radius graph, and then that is our graph that will be feed into the graph neural network. And the statistical approach, which is the module map, instead counts the number of particles that travels from one module to another. And after counting on a large set of events, we connect all the hits belong to two different modules that appears frequently in the statistics. And then next, with the graph, we can use GNN as an edge classifier and filter out all the fake edges. We then perform connected component search and regard the connected components as track candidates. And of course, we can improve the performance by walking through the graph, which means that starting from the root of each candidate, we select the most probable edge and walk to the next node and do that again. However, such a pipeline is still not perfect. The inefficiency and impurity that comes from the graph construction and purification steps leads to the so-called merged tracks and broken tracks. As shown by the diagram below, perfect matching only occurs while all the true edges are found and all the fake edges are filtered out. However, if there's impurity, in other words, false positive edges, then two tracks might be merged together. On the other hand, if there is inefficiency, then this will give rise to broken tracks, which means that the trajectory of one particle was broken into more than one pieces. Now, the problem is, could we remedy these defects with GNNs? Unfortunately, the answer was not. This is because that even though the graph after edge classification is both fairly efficient and pure, the inefficiency would forbid the two nodes belonging to the same particle from talking to each other. And this motivated us to use hierarchical GNN, which basically creates a new graph of supernodes. By supernodes, I mean that there are like the nodes in the upper level, which combine the lower level nodes together. Then the two ends of the graph will be able to talk to each other efficiently by hopping up and down on the hierarchical structure. And in order to do so, we would need a pooling algorithm that fits to our case. So what do we need? Firstly, we have to maintain the sparsity of the graph. Normally, the adjacency matrix of the graph is a sparse graph, is a sparse matrix, which means that the computational cost of performing graph convolution is proportional to the number of edges. And this is not as expensive as a fully connected graph, which is O(n) squared. And so that the sparsity, which is defined as the average number of edges connected to a node, must be controlled. And secondly, the algorithm must be differentiable. And if not, then the network is not learnable. Then we have to use some heuristic to pull the graph, which is something we would like to avoid because this would significantly constrain the possible form that the learned model might take. Finally, the number of clusters must be variable. This demand comes from a simple observation. We have indefinite number of particles in each event. And even though the model might not be learning to pull the hits belonging to the same particle together, this is still a good intuition and we should keep the number of clusters variable. So before jumping into my algorithm, there are a lot of related works in this area, and I would like to briefly discuss them and gain some inspiration from them. The first one is Diffpool. Diffpool proposes to use GNN to generate a probabilistic distribution S for each node to belong to each cluster. So this is like an assignment matrix. And after that, the supernode features is the weighted sum of the node feature, which will be given by S transpose N, where N is the node feature matrix. And the supergraph is attached with the super edge weights given by S transpose AS. Given a super edge and the two clusters connected by this super edge, the super edge weight is given by the conditional probability for the two ends of all the edges belong to the original graph to belong to the two clusters respectively, which will be given by S transpose AS. The next work is the Garnet. The input data has no graph structure on it. So instead of putting a full rank self-attention on such a point cloud, which will be very expensive, the author proposes to use aggregators and aggregates the node features according to a distance weighting function, which is called the potential function, and then pass them back to the nodes, again, weighting by the same potential function. So our takeaway here is that the hierarchical structure can communicate by passing S transpose N to the supernode updates and passing SX back to the node updates. The next task is to maintain the sparsity as well as the differentiability of this hierarchical structure. The GraphNet controls the sparsity by constraining the point cloud can only talk to their k nearest neighbor. And similar to Garnet, this is still weighted by the potential function. On the other hand, the top k pooling generates a scoring by using a GNN and select only the top k ranking ones. And obviously, this is a discrete operation. However, the differentiability is restored by multiply these nodes, the top k nodes, by the score gate. So they multiply the node scores to the original node features. So the takeaway here is that the sparsity can be maintained by using k nearest neighbor search, and the differentiability can be maintained by applying a score gate. Oh, sorry. So now I would like to propose my model architecture. So at the beginning, we have our usual interaction network update, which basically aggregates the edges to update nodes and aggregate nodes to update edges. And after that, we will embed all the hits into an embedding space and perform spatial clustering. And care must be taken here to maintain the sparsity and the differentiability of the supergraph, because typically the algorithm is not differentiable. So now we have an assignment matrix S and the supergraph adjacency matrix, and they are both sparse and differentiable. After that, we have the hierarchical GNN iterations. For the node updates, we have an additional input that concatenated to interaction ones, which is the supernode information. As discussed before, this is given by SX. And for the supernodes, the update is given by an additional input given by the node information, which is S transpose N. Both the edge and the super edge updates remain the same as the interaction ones. So even though it is intuitive that the requirement of variable number of clusters leads us to density-based spatial clustering algorithms such as dbScan, these algorithms produce only hard assignments, which is obviously not differentiable. So we have to address this issue. And the solution is using the idea of centroids. Given the node embeddings, we perform spatial clustering to get the cluster IDs. And so far, they do not have any gradient at this point. We then compute the centroids, which are basically the center of mass of each clusters. And the centroids are regarded as the supernode embeddings. Here, it's kind of like the reverse order, because like we are initialize the supernodes with the graph generated by these embeddings, while the usual process is to compute the embeddings from the supernodes. So our next step is to construct the supergraph and the assignments using these embeddings. The construction goes as follows. So given two sets of nodes and their embeddings, we construct the bipartite graph of sparsity k. Here, bipartite means that the edges only connects between the two parties, but not within them. And the sparsity of k means that in average, there are k edges attached to a node of A. So in the case of assignment, where we wish to assign each node to a set of supernodes, A and B are given by the nodes and the centroids respectively. And as for the supergraph construction, where supernodes are interconnected, they are both centroids, and the bipartite graph reduces to our usual notion of graphs. So firstly, we perform k nearest neighbor search and define the neighbor of each node of A as n of I, which consists the elements of B. Then we define the core distance, which is basically a normalized distance from the boundary of the neighbor to the embeddings. We then compute the edge weights, which we use a distance weighting function f of x and normalize them so that the edge weights around the node is summed to 1. So this function f can be chosen based on some intuition. Firstly, we hope that even if we are not applying a hard cut on the adjacency matrix, which is a direct result of building the graph with k nearest neighbor search, the edge weight is still changing smoothly from finite value to 0 as we go far from the center. This means that at the boundary of the neighbors, the edge weight should be 0, or at least close to 0. In other words, f of 0 should be close to 0. Another obvious requirement here is that the distance weighting function should be monotonically increasing. So for bipartite assignment between the original graph and the supergraph, we hope that the assignment is pseudo-single valued. So we use exponential function so that the edges, except the hard assigned one, are exponentially suppressed. As for the supergraph, we use hyperbolic tangent so that the solid links share almost the same weight. And in that case, a supernode can have multiple stable connections. Yeah, I think at this point, if anyone has any question, you can ask it before we jump into the result part.
So what's the application of this hierarchical clustering? Are you trying to construct the tracks from hits or construct the track jets from tracks?
We are, I'm connecting the dots into a track. So it's track reconstruction.
Okay.
So the intuition is that because the graph construction stage is not perfect, so we have inefficiency in our graph, which will forbid the two ends of the track to communicate with each other through the message padding step because there are some edges missing. Then building the hierarchy structure might be helping the two ends to communicate better because it will shorten the distance between the two ends.
Okay.
One way I thought about this when I was trying to understand what Ryan did, which is that, you know, there are different scales at which your graph may exchange communication. There could be a local scale, which is captured by the traditional message passing, but there is also a larger scale. And so the super graph structure makes sure that the information is passed with different length scales. Or message length scale. I don't know how to say it. Edge length scale.
Yeah, that's correct. Okay, so I guess I can move on to the results.
Sorry, one more question.
Okay. Sure.
So do I understand correctly that you are connecting these two levels of graphs and you're performing a single training so that the parameters are optimized simultaneously for the lower level and higher level graph. Is that correct?
Yeah, that's true.
Okay, thank you.
Oh, one quick question. So the super graph is based on the aggregate nodes, right?
Yeah.
Okay.
It is initialized by aggregating the node information based on the assignment matrix computed.
Okay, so that means that because like bottom is bipartite network, that means actually the hits are not interconnected, but hits only connect to the top level, then top level form a super graph.
Let me go back to this plot. So as you can see, in the lower half of the diagram, the hierarchical GNN iteration still preserves the original graph structure. It only concatenated the supernode information to the original input of interaction network updates.
Oh, I see. Okay.
Yep.
Yep. Got it. Got it. Yep. Thank you.
Okay. Let me move on to the results part. Oh, okay. So after all these descriptions, we would like to test our model. And unfortunately, I'm not able to show IDK results today. So I generated some toy events which contain 2D circular tracks. The graph is constructed to have specific efficiency and purity. The true edges are sampled from the edges that connects two adjacent hits of the same particle. And the fake edges are sampled from a fully connected graph. And the distribution of the radius of the circumcircle is made to be uniform. Our task is to find all the tracks that has R greater than 1. This requirement comes from the fact that R is a proxy of transverse momentum, since under uniform magnetic field, R is proportional to PT. And so we use hierarchical GNN for proof of concept and interaction GNN as a baseline. The loss function is defined as the hinge embedding loss. So first, we construct a fixed radial graph, and for each edge, the loss is defined as the Euclidean distance between of the two ends of the edge in the embedding space. And for the fake edge, it is defined as 1 minus that distance. The true edges are defined as those edges connecting two adjacent hits of the same particle. And there are also some neutral edges, which are the edges connecting the same particle but skipping some of the layers. And they are removed from training. And finally, the fake edges are defined as those connecting two different particles. Here are some results. Our evaluation metric, which is the tracking efficiency, is defined as the number of particles that occupied more than 50% of the assigned track candidate divided by the total number of particles. The experiment in the lab was sweeping over the number of particles in an event, and the one in the right was sweeping over different efficiency and purity configuration. And as we can see, hierarchical GNN is in general better than interaction GNN for a few percentages, and both of them scale pretty well with the number of particles. And as expected, for graphs that are pure, hierarchical GNN is more advantageous. This is expected since if the graph is not pure enough, then the pooling result might be confused by these impurities, and thus making the hierarchical structure not easily learnable. The last thing we're interested in is what exactly is the pooling algorithm learning, because so far we didn't use any heuristic. So here I show the clustering result we obtained when the model is constructing the supergraph. The coloring here is made to let those nodes close in the embedding space to share similar color. And as we can see in the diagram, it is really learning to cluster hits of the same particle together. And also, for those tracks that have similar curvature and location, they share similar colors, which implies that they are closer in the embedding space. Hence, they are more likely to be connected in the supergraph. The tracking efficiency, which is 44% here, obtained it at this point might seem to be low, but note that there is no loss function directly requiring this intermediate embedding to cluster tracks together. So this is already a fascinating result. And to see how the hierarchical iteration improves the performance, we compare the halfway result to the final result. And as we can see, the tracking efficiency improves by about 55%, and the fake rate is also dropping significantly. Even though we can't conclude that the improvement is solely coming from the hierarchical structure, since we still have interaction part in the hierarchical iteration, we can still see that the hierarchical iteration are really helping the model to cluster better. Here, I would like to end my presentation. There's an archive paper coming soon. Please stay tuned. Thank you.
So is your code available?
Yes, I have a GitHub repository, and I can send it in the chat. Thank you.
Thank you.
Thanks for the really interesting talk. Yeah, really cool to see. I was wondering if you've thought about doing like kinematic kind of feature extraction from the supergraph. So if you're aggregating, well, if you can, demonstrate that you're aggregating tracks into these super nodes, then could you do something like node value prediction on the supergraph to get things like the track like momentum or something? Is that something you've thought about at all?
Yeah, that is also possible. But one problem is that actually the assignment is not a hard assignment. So there might be the case where tracks is not assigned to a single cluster, or say a node in the original graph might not be single value assigned to one supernode. So if we are really want to extract, say, curve parameters from the supernode embeddings, then there might be some more modification to this model architecture needed.
So just double check. You only need like 2 layers, right? This hierarchy, like bottom is hits, and then the supernode sort of like a tracking or particle.
Yeah, in principle, you can stack any number of hierarchy if you want, but at this point, I think 2 layers of hierarchy is enough for tracking reconstruction.
Okay. Okay. Yeah.
Peng Yong.
Yeah, thank you. Because it's a neural network for the clustering, may I ask what's the loss of when you do the cluster? Loss function.
So
problem. Yeah.
So there are 2 clustering in this model. The first one occurs in the middle of the forward passing, and there is no loss function attached to this embedding space. But at the end of this pipeline, we embed all the nodes into another embedding space, and then use hinge embedding loss here, defined it as the Euclidean distance, or 1 minus the Euclidean distance, depending on the true or fake the edges is. Yeah.
Okay, thank you.
Can I ask a question? This is Daniel. Not just to you, Ryan, but like I guess to the crowd. Like obviously there's overlap here with object condensation and so on. And I think a lot of people are interested in doing all this stuff in one step, right? You take point cloud and then you cluster it into tracks and predict track parameters, vertex, just all one big step. But I haven't seen convincingly that you can kind of have your cake and eat it too. How do you cluster with these soft assignments and yet uniquely assign each cluster a set of track parameters when you could have multiple tracks in one cluster? I don't know if people have figured out how to do this in a like rigorous way.
But is that really, is that really the goal? The question is.
It could be one goal. Yeah, I don't know. I think it's a good goal.
It could be, but
Classes
are not clusters. That's otherwise we will be doing clustering and be done with.
But we should be doing clustering, I think, in some track parameter space, right? Like if there wasn't material effects, they would all uniquely be mapped to the same point in some high dimensional space, right? Okay, it's not perfect because you've got scattering and sort of weirdness, but
yeah, I mean, you have to do it, at least from all the different approaches I've seen, like you have to do some kind of like ambiguity resolution assignment that's like not perfect. So like we I mean, Gage can speak to the object condensation stuff, but we looked, you know, at one point at doing like instance segmentation kind of stuff where you're trying to use like some kind of bounding prediction, like bounding shape prediction to separate clusters in your latent space. And still, even then, like you have overlapping shapes, and so you have to make some kind of like decision about what you do. So I haven't seen anything that can get around that. Like you at some point have to interject your ambiguity resolution is like the term that I use, but something like that into the decision. So
I think it's pretty much dependent what your end goal of the application is. Yeah, if you thought of a trigger application that basically does a fast reconstruction of your entire event ensemble, counts the number of vertices and gives you the Q, or infers the momentum sum or something like this that on which you want to trigger. Then I think you'd get around without condensation or without hard assignment, because you could you do it at the end of the vertexing stage. Yeah, but if your application is really something where you rely on single object particle representations, you will have to do some sort of condensation, or you live with a weighted kind of multivariant system for your further analysis. Yeah, which one can also, I mean, the fact that we do 4 momentum physics at the end with always 1 4 momentum vector representing 1 particle is a choice that you condensate before this. Yeah, you don't have to condensate before this. You could do it on the analysis stage, but then it kind of starts smearing out the bound. You propagate the problem further down until you write a paper which has a probability density function underneath what it actually wants to say. Yeah.
yeah.
What's probably something we can discuss on the contrary is we know from pure principle detector resolution that we do have multiple node to track assignments if the hits are shared, which is the contrary, or the other side of this story, yeah, where you cannot easily rely on a one-to-one condensation at the end. Yeah, so I think this question goes in both directions from my point of view.
Yeah, I mean that piece of the puzzle, I guess, could be solved by like this soft assignment and some clustering where you can assign multiple nodes to multiple clusters. Yeah, but I agree, it's not obvious what the best way to represent this.
I can add this to, like, in object condensation, at least, even in the case that there's a shared hit, you still can at truth level just assign it to a track and then hope that overlapping tracks get condensed separately. And I think it's reasonable to expect that they can, because you're including in the back propagation, you're asking for like a physically meaningful track if you're actually asking for the track parameter prediction too at the end of the day. So you don't necessarily need a continuous track if you're doing object condensation. I mean, layer by layer, you can skip a layer and still have everything come together at the end of the day.
Yeah, in a soft assignment problem, you might actually, I mean, some people may remember what we have done in Atlas with the neural network clustering. We have a neural network that estimates then how many tracks contributed to the cluster and then assigns it. But this could be part of basically the graphs work to do. So you incorporate these handcrafted techniques that we have in several areas into a more single pass pipeline, which would have, I think, its benefits that you don't have to do single trainings on small little parts of your reconstruction software and then kind of hand engineer how they talk to each other. Yeah, so that's what we do. So good luck.
Shall we move on?
I don't know. You're the bad guy. You
It's
said.
not, yeah, I'm the bad guy. Actually, I discovered there is a later flight, so I can arrive almost very late.
Now we can stay here forever.
But perhaps any more, yeah.
If there's time, I did have a question about the talk. Yeah, so in choosing K for the KNN, I was curious what it seems kind of similar to just doing K rounds of message passing, right? Where you're asking that you aggregate information from the K hop neighborhood of each node. Here, you're just kind of speeding up the process by choosing for each supernode K nodes to talk to. So I was curious, in your comparison with the interaction network, how many rounds of message passing were you doing? And then what was your choice of K?
So the choice of K really depends, because like for the bipartite assignment, if the number of K increases, then it means that a node is assigned to more clusters, which means that of course, this might strengthen the model by, say, talking to more supernodes, but it might also confuse the model because you're passing too noisy, something that is too noisy, because you are using you're adding up those node features to aggregate your message. And so for this training, I set the K for the bipartite assignment to be 5, and the K of the supergraph to be about 20, and that is a hyperparameter that you can choose from. And as for the depth of the interaction network, I think for this specific training, the model gets the best result when I'm using 10 iterations, and after that, when the model gets too deep, it's just simply too hard to train, and the result is hardly converged.
Let's move on.
Okay.